Welcome learners. In today's lecture, we are going to continue our discussion on first order circuits. Previously, we looked into the working of the first order circuits where we looked into the behavior of the voltages and currents produced due to the natural response of first order RL and RC circuit. In today's lecture, we will continue our discussion and we are going to look into the step response of RL and RC circuit, and we are going to see what happens to the arising voltage and current equations when a certain voltage source is applied to the RL or RC circuit. So first we are going to have a discussion on the step response of an RL circuit. We are going to look into the mathematical expressions or the derivations which will guide us in understanding how the current is behaving or the voltage is behaving in RL and RC circuits. So till now we have seen in the natural response for the RL circuit that the inductor, whenever it is left alone with its resistor value and the voltage source was suddenly removed, so there was a flow of current happening in this circuit and this part of the circuit, and we got the expression for the current that depended upon the initial value I0 and exponential minus R by L into T, where we further set for the natural response that this could be written as time constant for T is greater than equal to 0. So this was the expression that we got when doing the natural response analysis of an RL circuit, and we saw that the response was making sense as if we plot the current response and the voltage response being similar, that after a certain amount of time the current will reach its final state final value or the steady state condition at 5 tau, because all of the energy stored by this inductor in the form of current will be released towards the load or the load resistor. Now let us see what happens when we suddenly apply a source to the RL network. So let us say that we had our inductor in the natural response and all of its energy got released and it has come back to its electrically neutral state, and then suddenly we apply a voltage source to this circuit, and now we want to see that is how this inductor is going to behave in terms of the arising voltages and currents. So now we have suddenly applied a voltage source to this inductor, and we are interested in finding the respective voltages and currents that are going to appear. This kind of configuration we already know is known as the step response of the circuit of RL circuit, because we have a resistor and a single inductor alongside it. So now if you look at the circuit, we can see that we have an independent voltage source V of S, we have the resistor R, inductor L which is suddenly getting a voltage source, and then we have a switch over here which is going to be in a closed state, or the switch is going to get closed at time equals to 0. If the time is less than 0, so if we consider for the time less than 0, we know that the inductor was placed separately and thus the current flowing is going to be 0 amps because all of the energy stored by the inductor has been released. So now let us focus what happens when time equals to 0, or we say it is also greater than 0, and we are going to do our analysis on this RL circuit. So when the time equals to 0, we say that the switch gets closed, which is the term of saying that the switch will keep closed for a long time. And we have previously seen that this long time indicates that a constant supply is being given, constant supply of energy, whether it's coming from the voltage source or the current source, is being given to the inductor. And we know that if a constant supply is given to the inductor, it will reach or it will act as a short circuit. But we want to see what happens immediately to the currents and the voltage when the switch gets closed, and then later on we are going to look into the long time analysis. So let us solve this circuit. We can see that as soon as the switch gets closed, the current will start to move, and we can define the flow of current in a clockwise direction. Now let us solve this and figure out the equations for the respective currents and voltages and see its graphical behavior. So let us apply KVL to this circuit, and we can start from, let's say, any node. I'm selecting the bottom left, let's say point A to be my node. So I can write KVL is equal to V of S plus V of R. Then we follow through the switch, and then we reach the voltage at the inductor equals to 0. Now if we further simplify the equation, so V of S equals to V of R plus V of L equals to 0. Now let us input the values of the respective voltages. V of S equals to, voltage will be IR as per Ohm's law across the resistor, and voltage at the inductor is L di by dt equals to 0. So now let us get rid of this inductor by dividing it by L. So this will be cancelled out. So we will be left with d of I by d of t plus IR by L equals to Vs by L. And this is the first form of equation that we are getting. And if you look at this equation, this is basically not equal to 0. Rather, we technically call this as a non-homogeneous equation, or non-homogeneous first order differential equation. So now there are different ways to solve this non-homogeneous equation and convert it into a homogeneous form. We can continue with the derivation or differentiation, or we can try to bring it in the form of a homogeneous equation where the equation equals to 0. So let us try to turn this non-homogeneous equation into a homogeneous one, which means our equation should equate to 0. So in order to do this, let us try to simplify the equation. So let me write it, equation 1 as di by dt plus IR by L minus Vs by L equals to 0. So now I'm going to use this site for further expression and derivation. So let us factor out few things. Di by dt, I'm going to take R by L as a common factor, which will leave me with I minus Vs by L, and now I'm going to inverse the fraction of R by L into L by R, and thus is it equal to 0. And though this is known as the inversion fraction rule, where I have inverse the fraction R by L into L by R, and we can verify that this conversion is right if we just multiply RL inside the parenthesis. So we should get this same expression over here, and thus this inversion is verified. So once we did this inversion, we can easily get rid of the inductor value, and thus our equation will be di by dt plus R by L I minus Vs by R equals to 0. Now let us do some substitution method to simplify this equation further. So let us consider this parenthesis to be u, then my du by di equals to 1. So which means my new equation or simplified equation then becomes di will be replaced by du divided by dt plus R by L multiplied by u equals to 0. So this is where di is getting replaced by du. So now let us rearrange the values and get rid of this d of t. So I can write du by dt multiplied by dt equals to minus RL u multiplied by dt. So this d of t cancel out. I can bring this du or u back over to the left side of the equation, and thus I will get this form of the equation. And now we see that our equation is resembling to the same expression which we saw during the expression derivation in the natural response behavior. So my equation in its true form is now converted into a homogeneous equation if I write it as like this. So I can have my equation written like this. Now once I have this, I can easily start to figure out the value of the currents by integrating this whole expression. So what I can do is if I integrate the expression and use the relative terms, so I can write integrate u of t naught to u of t. These are my initial to final limits. This will become du by 2, and I can write minus r by l, and then the limits will be from 0 to t d of t. Now we can simply go about in the integration. So 1 by u is natural log of u of t minus u of t naught. So I've just input the values of the limits, minus r by l. Integral and differential will give you a value of t. Once you put the limits of 0 to c, so you should get the value of t. Then this natural log property of subtraction can be written or can be transformed into a fraction, which is equal to minus r of l into t. So let us now get rid of this natural log by multiplying it with an exponential on both sides. And once we do this, the natural log cancels out, so we'll be left with u of t, and I can take this u of t to the other side, and when the exponential gets multiplied by this factor, so it becomes as a power of the exponential as per the mathematical rule. So this will become u of t naught e raised to power minus r by l multiplied by t, and this is my equation number 2, which I am getting in a simplified form. So now once I have these values in terms of the u of t, let us substitute back the value of u, which previously was I minus v by r. So substitute this value back into the expression. So I can use this space now. So let us substitute back values of current. Substitute the value of u back into the equation, back into equation number 2. So if the equation was u of t equals to u of t naught e raised to power minus r by l into t, so we know that u of t will become I of t, as this is the equation, I minus v by s by r. So I of t minus vs by r equals to u of t naught basically means at time instance of 0, so it is going to be a 0 value. So I can say it will be I of naught minus vs by r, and you multiply it e raised to power minus r by l into t. Now what about this expression? So we know that this is similar to the time constant. So we know that the time constant for an RL circuit is the ratio of the power of the exponential, which is r by l. So this comes out to be l by r. So we can write this as a tau term as well, and the time constant remains the same, where time constant is basically pointing us that at how much time a system is going to take to reach its steady state condition, and this is what we saw previously. So if I refine this equation for current, I can write I of t equals to I naught minus vs by r e raised to power minus t by tau, and then I can bring vs by r from the other side, and this is the expression for the inductor current, which is basically going to let us know that how much current is flowing inside the RL circuit when a sudden voltage source gets applied to the inductor, and this is the behavior of the current for the RL step response. And if we want, we can further simplify the equation. This equation A can be simplified further if we know that our initial current was 0 amps, as we have already considered over here. If we look at the condition when time was less than 0, we know that the inductor was as a separate entity and all of the energy got released by the inductor. So the initial condition for current 0 is, if you remember, we took I0 negative equals to I0 plus, and it should be I naught, when in this case is 0 amps. So we say that the initial current for our case is at 0 amps. So then this equation can further be simplified. So the inductor current comes out to be Vs by R, and this will be a negative Vs by R e raised to power minus t by tau. So this equation B is also a simplified version of the first equation, and these two equations are used side by side or for solving the currents inside the step response of a system. Now let us look into this equation and see what analysis we can do based on this equation. So we can see that this equation is basically telling us that the flow of current inside the inductor is wholly and solely dependent upon the ratio of the voltage and the resistor. The inductor itself is not contributing into the flow of current, because we know that when the switch gets closed after a long time, if we go back to our circuit, we know when this switch it gets closed at t equals to 0, and after certain time the inductor is going to behave as a short circuit. And again, it is also verified through this final expression of current that the inductor's value, or L, is not contributing in the flow of current. The current is only controlled by this voltage source and this resistor, and later on we can see that this can be simplified into a Thevenin resistance as well, or Thevenin voltage. But for the time being, we are just focusing that the final current of the inductor is just controlled by the ratio of the voltage and resistor. And thus, if we want to plot this equation B and see the response of the current, so we can say that this is basically a current that is linearly or exponentially increasing. So let us say our horizontal axis is the time scale and our vertical axis is the amount of current. So if we put the value of tau in equation number B from 0 to infinity, we should get the following graphical representation, where we know that if we put at time is equal to 0, and we know that for time less than equal to 0 there is no flow of current, so this will remain as 0. At time is equal to 0, we again get the value of Vs minus divided by R minus Vs R equal to 0, so this is equal to 0. And at time is equal to infinity, so if we put infinity in the power of the exponential, the only thing left will be Vs by R, and thus we can say that the behavior of the circuit is going to be something like this. So the maximum value that the current will have will be Vs by R, and the initial value will be 0, and thus after a certain time, which we call as 5 time constant, the system is going to achieve its steady state condition. So this is going to be the behavior of current, and we can again see that the inductor is not going to affect the behavior of the current, rather it is going to act as a short circuit. And also from the graph we can see that for the first value of tau, we can say that the circuit is basically going to have 63% of its energy being utilized to reach towards the steady state condition. So this is the behavior of the current inside the inductor, where see there is an exponential increase and it reaches to the steady state value of 5 tau, which is the maximum value of Vs by R. So now once we have figured out the behavior of current, let us see what is going to happen to the voltage. So this was the current behavior. Now let us put our attention to the voltage of the step response. So now how the voltage is going to behave this circuit. So let us look at the voltage behavior of an step response of an RL circuit, and then compare it to the response of the current that we have seen over here. So we know in order to find the voltage in an inductor, we know it is equal to L di by dt. So we can say that voltage is equal to L di by dt, where the value of current from equation A comes out to be I naught minus Vs by R e raised to power minus RL multiplied by T plus Vs by R. So when you differentiate it with regards to the current, so this is a constant, it will become equal to 0, and here we can apply the equation of, since this is one entity and this is a second element, we can apply the dot product or u dot v, where the differentiation of u dot v is equal to u differentiate v plus v differentiate u. So when we apply this property, the equation, the final output equation for the voltage inside the inductor VL of t should come out to Vs minus I naught R e raised to power minus RL multiplied by T, again condition for greater than equal to 0 plus. So this is the voltage equation that we are going to get for the inductor, And if you want to further simplify this equation by considering I naught is equal to 0 amps, so this is my equation number C. So this equation can be further simplified to Vs e raised to power minus R by L into T. So this is equation D. So again we have two representations of the voltage inside the appearing across the inductor, and thus if we want to plot this equation D, we can again see the behavior of this voltage. In order to see the behavior of the voltage, we can keep the value of time from 0 to infinity, and when we put the time of 0, we get a very strange behavior. That let us plot the voltage behavior over here. So this is the time axis and this is the voltage that we want to know inside or across, appearing across the inductor. So when time equals to 0, the only thing left will be V of S, and when we put time is equal to infinity, we get a value of 0. So we can see that when the time was less than 0, there is nothing over here, and as soon as we reach time is equal to 0, we see a sudden jump towards a maximum value. So previously we talked about inductors, that inductors don't allow the abrupt change of current, but we can see from here that as soon as the inductor starts receiving energy from the voltage source, the first thing that it encounters is a maximum value of the voltage source, and which we can also justify, like if we have the same circuit where we have a voltage source followed by a resistor and then we have an inductor, and this was the switch that we had. So at time is equal to 0, we can immediately see that when the switch gets closed, our equation for inductor voltage comes out to be the difference of Vs minus Vr. So we know that Vs is the voltage source, and the current that we are going, or the according to Ohm's law, the voltage across the resistor is going to be the initial current multiplied by the resistor. Since the initial current is 0, the only thing the inductor is going to have at time equals to or greater than 0 is going to be the maximum voltage source V of S, and thus we are getting the same behavior graphically shown and mathematically proven as well. So when we put the time equals to 0, so the voltage is going to behave something like this. So we say that after certain 5 tau, the voltage is also going to have its steady state condition. So if we see the current and the voltage graphs side by side, so this being the current's behavior, which was linearly increasing till it reached its voltage or steady state condition, and so this was basically the steady state condition. And for the voltage, we also see that at 5 time constant, it has reached its steady state condition. So we come to this realization that when a step response behavior is applied, the inductor is basically going to have a leading lagging in terms of the voltage and current that arise in the system. So we can say that in the case of a step response of an RL circuit, here the voltage is leading the current, or normally we represent it as an acronym of ELI, where voltage leads the current in the inductor, and it can be graphically seen that at time 0 the value of voltage is maximum. Similarly, at time 0 the value of current is at the lowest one, and hence we can say that when a step response is applied to an RL circuit, the voltage leads the current. So this concludes our discussion on the step response of an RL circuit, and next we move to the step response of RC circuit. So now let us talk about the step response of RC circuit, and let us see what is going to be the behavior of voltage and current when we have the RC circuit with us. So in order to analyze the RC circuit, we can go about the same derivation lines as we saw now with the RL circuit. So in order to have a step response, we can say that we had a capacitor, and when it was in its natural behavior, it gave away all of its energy in the form of charges, and after a certain amount of time, we applied a certain source to it. Let us say this time it was a current source. So this is our switch. So at time is equal to 0, this current source is going to create the amount of charges across the capacitor. So when time was less than 0, we can say that the initial voltage, which we consider to be equal to the final voltage, is basically 0 volts. So V naught is basically 0 volt when the time was less than 0. In the time of less than 0 means that in this case the switch was open. So now when we reach towards time equal to, or we say greater than 0, the switch basically gets closed. When the switch gets closed, our circuit will be something like this. Now the current will start to move and it will enter the capacitor, and again there is going to be a gradual increase of charges being accumulated on the plates of the capacitor. So let us apply KCL for the analysis of current. We consider this as our node. So when we apply KCL to the circuit, and we are doing this to figure out the equation for the voltages and the currents on this RC circuit. So when we apply KCL, our equation will be I of S is entering the node, so we consider minus I of S. Then the current leaving the resistor is plus I of R, and then the same current is going through the capacitor. So we can say plus I of C equals to 0. So we can say I of S equals to Ohm's law V by R plus the current in the capacitor is C dV by dt equals to is equal to dV by dt. So to get rid of this capacitor, we can divide it by C. So our equation now looks as dV by dt plus V by RC equals to IS by C. This is our equation number 1, and again we can see this is of the non-homogeneous form, as we saw previously with the RL circuit. So non-homogeneous first order differential equation. Let us convert this non-homogeneous equation into a homogeneous one. So what we can do is we are going to write it again in the form of dV by dt plus V by RC minus IS by C equals to 0. Then let us take 1 by RC as a common factor. So dV by dt 1 by RC, in the bracket parenthesis we'll have V minus inverting the fraction will be RC multiplied by IC by C equals to 0. So this capacitor or capacitance value will cancel out, and thus our equation will be dV by dt plus 1 by RC V minus R I S equals to 0. So this is the equation that we are having with us now. We have tried to equate it to 0. Now let us do the substitution method, where let us assume that this is value of U. So then du by dV equals to 1. So let us input all these values to the above equation, and thus we will have d will be replaced by du by dt plus 1 by RC, and this becomes U equals to 0. So now we have substituted the values of U inside our circuit, and now we can go about by doing the integration as we did last time. So we go as du by dt, but first let us get rid of this d of t, minus 1 by RC multiplied by U into dt. So this dt cancels out. I'll bring this U back to the other side. Du by du U is equal to 1 minus RC dot dt. Now let us integrate it from 0 to t, and U of t naught from initial to U of t final value. Again, when we integrate this, we know that 1 by U is basically ln, and the limits, let us put the limits as U of t minus U of t naught equals to 1 divided by RC, and this becomes t with the limits already incorporated into this. So this expression will be log of n, and the subtraction becomes a fraction is equal to 1 minus RC multiplied by t multiplied with an exponential to get rid of this natural log, and this whole term as per rule becomes the power of the exponential. So I can finally write that u of t equals to u of t naught. I have moved u of t naught from the denominator to the other side, e raised to power minus t by rc for t greater than or equal to 0. Again here the time constant comes out to be r of c. So finally we can substitute back the value of u of t which was considered over here. So our equation then simplifies to v of t minus is by r equals to v naught minus is by r. Again u of t is at time instance of 0, e raised to power minus t by rc. So finally the voltage at the capacitor is equal to v naught minus isr e raised to power minus t by rc plus is by r for t is greater than 0 or equal to 0. So this is the governing equation to find what is happening to the voltage when we have the step response. And we can also simplify this equation if we consider the initial voltage to be 0. So this equation, let me call this equation as equation 4, can also be simplified as the voltage appearing across the capacitor is going to be ISR minus ISR e raised to power minus t by rc for t is greater than or equal to 0. So this is again the second representation of the above equation 4, and let me call this equation 5. Similarly, we can find the current of this behavior. So we know that the current across the capacitor is equal to C dV by dt. Just incorporate the value of V from here. So the final equation for the current will be C dV by dt can be written as 1 by RC V naught minus 1 by SR e raised to power minus 1 by RC into T. So this capacitor cancels out, and the current at the capacitor and this is equal to Is minus V naught by R e raised to power minus T by RC for T greater than equal to 0 plus. So this is equation number 6, or which we can say we used to figure out the currents flowing through the RC circuit. And finally, if we want to plot the behavior of this voltage and current, so we can see that if we put the value of time for both the cases from 0 to infinity, then the plot for both of these cases will appear something like this. So if my horizontal axis is the time scale and vertical is for the voltages and currents, so let me use green for the voltage and red for the current. So now if we plot the voltage behavior, we can see that at time is equal to 0, when the time is less than 0, so this is the time which is less than 0, and this is the time greater than or equal to 0. So we can say for less than 0 everything remains 0 because the capacitor is not receiving any energy and it has already discharged its energy. So this is what we have at time equals to 0. It's a flat line. Okay, and now if we come to point at t is equal to 0, so this is the point at t is equal to 0, we get a value of 0 because this equation will become 0. So if we put time is equal to infinity, the maximum value we get for the voltage is going to be Is of R. So we can say that the voltage is going to be a linear rising function. It is going to be something like this. So this is the maximum value of Is of R for the voltage, and after certain time which we call as 5 tau, it is going to reach a steady state condition, and that steady state value will be ISR. What about the current? So at time less than 0, there is going to be no current, and as soon as we open the switch, we can see for the current at time is equal to 0, we will reach a value of Is. So let us say this is the value of Is, the maximum value for current, and the current is going to basically have a behavior as such. And again, it is going to be having a steady state value after 5t. So we can see that the current is now behaving opposite to the voltage, or they are 90 degree apart, and we can say that in this scenario the current is leading the voltage, which we normally represent as an acronym of ICE, where current leads the voltage in capacitor, and we can see the representation graphically of both of the elements. So this is basically how the step response was for an RC circuit, and we saw this step response of the RL circuit as well. Now let us look towards an example and see how we can solve problems associated with RC and RL circuit. Let us look at an example on how to solve or understand how the step response of RL or RC network works. So in this example, we have basically been given this circuit shown over here, and we can see in this circuit we have an independent voltage source of 24 volts, then we have a 2 ohm resistor, and then we have a switch. Currently the switch is at position A, and when time equals to 0, this switch is going to move from position A to position B. Then we have an inductor of 200 millihenry followed by a 10 ohm resistor in parallel, and then we have an independent current source of 8 amps. So in this problem, we have been asked that initially that the switch has been closed for a long time. When the time reaches to 0, the switch moves from position A to position B. This kind of a switch is known as a make before break type, because we don't want to have a sudden change of current, because it will lead to the voltage being infinite. So in order to avoid this infinity problem, we make these kind of use of these power electronic switches. So now when the connection is established at position B before the connection is broken, that's where we call it as a make before break type. So we have been asked that what happens to the inductor, and you need to figure out these 5 unknowns starting from point A to point B. So let us try to solve this one step at a time. Let us take the first solution of the first part, So we need to find the expression for the current when the time is greater than equal to 0. This means that when the switch has been moved from point A to point B. So, but before we can go about this, we first need to know the equation for the current in the step response behavior. So the equation for the current flowing through the inductor is basically dependent upon I naught e raised to power minus R by L, or this is basically the equation when we had the value of natural response, but now we are looking into the step response. So the equation for this comes out to be I naught minus Vs by R e raised to power minus R by L multiplied by T plus Vs by R. So this is the equation for the step response behavior of an RL circuit. So in this equation, first we need to figure out what is I naught, which is the initial current. Then we will look into the values of the Vs by R, exponential minus R by L. This R by L is basically the tau value of L by R. So we can find the time constant from there for the exponential, and then the remaining values will be the similar for Vs by R. So in order to find I naught, we first have to see what happens to the circuit when time is less than 0. So when time is less than 0, we have this form of a circuit where this position of the switch is at point A. So we are only having an inductor followed by a resistor, and then we have the current source of 8 amps in the downward direction. This is 10 ohm and this is 200 millihenry, and the flow of current is from positive to from top to down, and the voltage is appearing over here. So we need to first figure out what is the value of current when time is less than 0. So when the time is less than 0, we know that the switch has been closed for a longer time. So when the switch or when the current source is being applied for a long time, all of this 8 ampere current will appear across the inductor, and since it's a constant source, so this is going to act as a short circuit. where the voltage will be 0 and inductor will have the maximum value of 8 amperes of current, which we are calling is at I0. But one thing to remember is that the direction of the source current is towards the downward, and the direction of the inductor current is also given to be in the downward direction. This means that this 8 ampere current will enter from the negative side and go in the upward direction, which means as per the passive sign convention, our current should be minus 8 amps. So this is an important point to remember, since the direction of current and the signs define where the value of the current will be, whether it will be a positive sign or a negative sign. So the initial current I0, which is going through the inductor, is going to be a negative 8 amps. Now when time is greater than equal to 0, let us now do the analysis. When time is greater than equal to 0, we enter into this step response, because the position of the switch will move from point A to point B, and thus our new circuit will be a voltage source connected to a resistor, and then we'll have our inductor. So this will be 24 volts, this will be 2 ohm, and this will become again 200 millihenry. The direction of flow of current is again in the downward, and at this stage we know that minus 8 ampere is already initially over here. So this is basically the 8 amperes. But now we want to know what happens when the switch closes and what is the new value of the current. So again, now the current is moving in this direction. So the new value of current comes out to be V by R, which is 24 by 2. This is 12 amps. So we can see now the current has changed from the initial value of minus 8 amps to 12 amps when the switch is closed, or the switch moves from position A to position B. Thus, we now need to find the time constant so that we can find the current based on this equation. So let us use this side over here. So the time constant is the ratio of inductor over resistor. Here the inductor is 200 millihenry and the resistor is 2 ohm. So it comes out to be 100 milliseconds. So this is the time constant that we have. So finally, when we input all the value of we have into our inductor current equation, so ILT was I0 minus Vs by R e raised to power minus t by tau plus Vs by R. So we know that the current is minus 8 minus 24 source divided by 2 e raised to power minus t by 100 millisecond plus 24 divided by 2, and the final response that we should get will be 12 minus 20 e raised to power minus 10t amps for time greater than equal to 0. Remember, you have to put in the conditions so that we know that in which portion of the circuit we are operating. So t, it should be greater than equal to 0. So this is how we basically got the expression for the current, or the first part is now solved. Now let us come to the second portion. In the second part, we have been asked that what is the voltage that is going to appear. So in the second portion, we want to know what is the initial voltage across the inductor just after the switch has been moved to position B, which means that we are in time equals to 0 or greater than 0. So in order to find the voltage, we just apply the basic equation that voltage is equal to di by dt, and once we simplified this earlier, we got the equation as Vs minus I naught R e raised to power minus t by tau for t greater than equal to 0 plus. So now the voltage across the inductor comes out to be 24 minus 8 into 2 ohm e raised to power minus t by 100 millisecond, and it comes out to be 40 e raised to power minus 10t volts. 40 is greater than 0 volts. So this is the voltage that is going to appear on the inductor when the switch has just been moved from position B to position A, or we can say this is when the system is behaving in the step response circuit. So now we have figured out the voltage, but now I have been asked what is the initial voltage, and it is just the voltage that is going to appear when the switch moves. So for initial voltage, we know that we have to take t equals to 0. So t will be equal to 0, just input t equals to 0, so we get V of L of t is equal to 40 volts. So this is the initial voltage that just appears when the switch is moved from position A to position B. So now let us see what happens. So in the third part we have been asked that does this initial voltage make sense in terms of the circuit behavior? So what does it mean? So let us look at the third part. In the third part we have been asked a logical question that as soon as the switch has been moved from A to B, the voltage or the initial voltage was 40 volt, but currently when we are at position B, the voltage is 24 volts. So does it make any sense? So let us see what we can do. We know that the initial voltage was 40 volt just after the switch has been shifted, but prior to that we knew that the initial current I naught that was available at the inductor was minus 8 amps. When we move from position B to position A, the voltage, so let me draw the circuit to make it more easy. This is 24 volt source and this is the inductor. This is the voltage source of 24 volts. This is 2 ohm and this is the inductor that we had. And this is basically position B. And let us assume this was position A. So the moment we switched from A to B, we know that initially the current at the or available or flowing through the inductor was minus 8, and later on this changed to 12 amps as we saw previously. But when this current was 8 amps, the initial voltage also came out to be 40 volts. So does it make any sense that on the right side we had a 40 volt and then the source applied is 24 volts? Logically 40 volts should supersede the 24 volt source, but this is something like this, that initially if we had minus 8 amps, what was the voltage appearing across the 2 ohm? So voltage initially across the 2 ohm as per Ohm's law should be IR. The current was minus 8 and the resistor was 2, so this is minus 16 volts. So we can say that initially minus 16 volts was being circulated in this direction, and then when we do the comparison of the total voltage available inside this circuit, we can see that the V total comes out to be 24 volts minus 16 and it is 40 volts. So we can say that the initial value of 40 volts is the same value which is available throughout this circuit over here. So the 24 volt is justified as it is some of the portion that is being there when the step response happens, but the 40 volt that came from the initial behavior equals to the difference of 24 with 16 volts, and thus we can say that this initial condition value of 40 volt makes sense because when the switching happens from A to B, the minus 8 ampere currents is creating that additional voltage, and thus the 40 volt value on both the side remains the same. So this is how this is happening. So now let us go to the next portion of the problem, that how much time in millisecond it takes the switch to induce the voltage or have the voltage of 24 volt. Basically we have been asked that how much time the switch is going to take to move from A to B, thus that we get 24 volts across this 200 milliohm inductor. So in order to solve this, we again take the help of the initial voltages and the new voltages. So we know that the initial voltage was 40 volts and the value came out to be minus 10 tau, and the new voltage when the switch move is 24 volts. So we can figure out how much time it is going to take. So we can write e raised to power minus 10t is equal to 24 divided by 40. In order to get rid of this exponential, multiply it with a log or a natural log. So this cancels out. I'll be left with minus 10 of t is equal to 24 divided by 40 multiplied by natural log, and then the time comes out to be you divide this by 10 or you make it more simple, 24 divided by 40 multiplied by the natural log divided by minus 10, and the time comes out to be 51 milliseconds. So this is the amount of time taken by the switch or the inductor to move from the voltage of 40 volts to the value of 24 volts. And in the final part, we have been asked to plot the current and voltage behavior of this step response circuit. So it is going to have a response as such. So let us say this is the behavior that we want to know. This is the time axis from 0 to t. We know when the time is less than 0, everything is 0, and this is in terms of tau. So t to 5t, and this is the portion when the time is greater than equal to 0, starting from here and going for covering from here to that point. So let us first draw the voltage behavior. In order to draw the voltage behavior and the current behavior, we need to write the final equations that we have. So for the voltage, we can say that let us write the equations for the current. So this is my portion. So the current's value that we got was 12 minus 20 e raised to power minus 10t. So 12 minus 20 e raised to power minus 10t for t greater than equal to 0. And for the voltage, we got the value of 40 e raised to power minus 10t for t greater than equal to 0. So for both of these cases, just put the value of time from 0 to infinity and we should get our behavior. So let us first draw for the current. When time is 0 at 0 axis, we get the value of, so e raised to power 0 will be 1, and then we have 12 minus 20, so this is let us say minus 8, and then if we keep on increasing the value, we get to minus 4 and so on till we reach 0. Similarly, the scale on the upper side will be the same, so 4, 8 and 12, and then for the currents. Okay, and so we can plot this, then we know that this is going to be a linearly increasing function. So the behavior of the current is going to be something like this, and this is the time where it becomes 5t, and this is a saturation point. So this is the current behavior that we are going to have starting from -8. And what about the voltage? So for the voltage, we are going to put e raised to power 0. So we know that when you put the value of 0, you get the maximum value of 40 volts. So let us say if I extend this to be 40 volts, this is going to be the maximum value, and when you put t is equal to 0, you will be 0. So we can say the voltage is going to decay exponentially like this, and this is again the threshold for it. So this is going to be the voltage graph. So this is for VL of t, and this is for the IL of t. So this is the plot or a comparison between voltage and current, and we can see that the voltage is leading the current in this scenario. And thus this concludes our today's lecture on step response of RL and RC circuit.